For this question, we want to graph the function f of x equals x plus 2 times x plus 2 over x squared minus 36. So this is called a rational function because we have a variable in the denominator. So there are a bunch of things that I want to pull together in order to understand what the graph of this function is going to look like. So I'm going to start with finding the domain of this function. Finding the domain of a rational function requires me to set the denominator equal to 0 and solve. So I'm going to isolate the square by adding 36 on both sides. That gives me x squared equals 36. And I'll square root both sides and get x equals plus or minus 6. So these are our restricted values, and the function is not defined at these values. So I'm going to think of my number line. This is the real number line. We'll mark -6 and +6. Our restricted values are -6 and +6, but every other number on this number line will be a part of the domain. So we can write that domain in interval notation. We would represent each one of these intervals, writing a lower bound and an upper bound for each shaded region. So we would have -∞ to -6, union with -6 to 6, union with 6 to infinity. So our domain is all real numbers except for -6 and +6. And we write that in interval notation as -∞ to -6, union with -6 to 6, union with 6 to infinity. So now that we've identified these restricted values of -6 and +6, I want to know what kind of restricted values they are. So they can be holes in the graph or they can be vertical asymptotes. I want to know which one is -6. Is it a vertical asymptote or is it a hole in the graph? Same thing with 6. And the way that we determine that is by writing our function in factored form. So I write the numerator in factored form. This one happens to already be factored, x plus 2 times x plus 2. And our denominator is a difference of squares and can be factored. That's x plus 6 times x minus 6. Once we write it in factored form, we're going to be looking for common factors between the numerator and denominator. I can see that there are no common factors between the numerator and denominator, and that means that there are no holes in the graph. And that tells me that these restricted values of x equals -6 and x equals 6 are both vertical asymptotes of the function. Knowing that these are vertical asymptotes tells me that as x approaches -6, y is either going to approach infinity or negative infinity, and as x approaches 6, y will approach infinity or negative infinity. This is very important to understanding how to draw the graph near those spots. The next thing that I'd like to look for are any horizontal asymptotes. And horizontal asymptotes are the end behavior of the graph. These are what is happening as x approaches infinity or as x approaches negative infinity. So this is going to tell me how to draw the graph near the end. Now, to find these horizontal asymptotes, I need to know the degree of the numerator and the degree of the denominator. So we call the degree of the numerator n and the degree of the denominator m. So this one is a little interesting since it was written in factored form. It might be a little bit more difficult to find the degree, but if you can imagine multiplying out this x plus 2 times x plus 2, you would get x squared as your highest power of x. You would get x times x, which is x squared, x times 2, which is 2x, 2 times x, which is 2x, and 2 times 2, which is 4. The highest one of those would be x squared. So the degree of the numerator is 2. And then in the denominator, we also have a degree of 2. So once we know the degree of the numerator and the degree of the denominator, we need to decide which case of horizontal asymptotes we're in. So there are 4 cases, and the 4 cases are where n is less than m, the degree of the numerator is smaller than the degree of the denominator, the degree of the numerator is equal to the degree of the denominator, the degree of the numerator is 1 more than the degree of the denominator, and then finally, this is covering all other situations where the numerator is larger, but larger by 2 or more. So you can see that since we have the degree of 2 in both the numerator and denominator, we're in the second case where the 2 are equal to each other. So we have a rule that we memorize about this case. And the rule is that the horizontal asymptote is y equals the ratio of the leading coefficients. Now, the reason why we memorize a rule is because the actual math behind finding the horizontal asymptote involves an operation called limits, and that is a calculus operation. And we're in an algebra class, so we're going to find it by this technique of recognizing the different cases and memorizing the rule for that case. So we're almost there in finding the horizontal asymptote. We just need to know what is the ratio of the leading coefficients. So the leading coefficient for the numerator will be 1, because when we multiply x times x, we get x squared, and that coefficient will be a 1. And the leading coefficient from the denominator is 1. And so we're going to do the ratio of those leading coefficients, and we have our horizontal asymptote being the line y equals 1. So as x approaches infinity, or as x approaches negative infinity, y will approach the value of 1. That's going to tell us how to draw the graph. At the ends, y will be getting closer to a value of 1 as x goes to infinity and negative infinity. The next thing that's important to know is if the graph ever crosses the horizontal asymptote. So in order to figure out if the graph crosses the horizontal asymptote, we're going to create the equation where the function or the graph equals the horizontal asymptote. So our function is x plus 2 times x plus 2 over x squared minus 36, and the horizontal asymptote is 1. So we're going to create this equation and solve the equation, and that will determine if our function ever crosses that horizontal asymptote. So to solve this equation, I'm going to multiply by the denominator on both sides, multiply by x squared minus 36 on the left, and x squared minus 36 on the right. That's going to cancel out the denominator on the left, leaving me with x plus 2 times x plus 2. And on the right, I have x squared minus 36. I'll multiply out x plus 2 times x plus 2. That's x squared plus 2x plus 2x plus 4 equals x squared minus 36. If I subtract x squared on both sides, the x squareds cancel each other out. And I'll go ahead and combine 2x plus 2x is 4x plus 4 equals negative 36. I can solve for x by subtracting 4 on both sides. That's 4x equals negative 40. And I'll divide by 4 to get x equals negative 10. So the graph will cross the horizontal asymptote. It's going to cross at x equals negative 10. Now this will be a point, negative 10, and the y value of that point is going to be on top of the horizontal asymptote. So that y value of the point is is 1. So the point is negative 10, 1. So now we're going to look for any x and y intercepts of this function. To find a y-intercept, you're going to let x equal 0. I'm substituting a 0 into the function, and that would be 0 plus 2 times 0 plus 2 over 0 squared minus 36. So that gives me 2 times 2 over negative 36. 4 over negative 36 would reduce down to negative 1/9. So we do have a y-intercept, and that is the ordered pair 0 and negative 1/9. And let's find our x-intercepts. To find x-intercept, you're going to let y equal 0. This function is written in function notation, and so instead of using y, we have f of x. So we're going to set f of x equal to 0. So we have the equation 0 equals x plus 2 times x plus 2 over x squared minus 36. To solve this equation, we'll multiply both sides by the denominator. And x squared minus 36 times 0 is 0. And the x squared minus 36 cancels on the right. And we have x plus 2 times x plus 2. This is already in factored form, so we can use the zero product property and set each factor equal to 0. We have x plus 2 equals 0 and x plus 2 equals 0, and that will give x equals negative 2 and x equals negative 2. Those are the same value, so we get the ordered pair 0, negative 2 as our x-intercept. And I wrote that incorrectly. Let me fix that. I wrote that as a y-intercept. That should be the ordered pair negative 2, 0 as our x-intercept. So I think we are almost ready to graph. I'm going to put down a grid for us to draw the graph on. And we're going to start by marking out some of the information that we found previously. We found that we have two vertical asymptotes occurring at x equals negative 6 and x equals positive 6. So I'm going to mark out at x equals negative 6 a vertical asymptote. So I'm drawing a dashed line. This dashed line is going to act as a guide to help me draw the graph, but I have to remember the definition of the vertical asymptote to do that. So we want to remember that the y is going to either go to infinity or negative infinity at these vertical asymptotes. So I'm drawing those vertical dashed lines at x equals -6 and +6. Then we also had a horizontal asymptote. The horizontal asymptote is at y equals 1. So I'll draw a horizontal dashed line at y equals 1. So we have to remember the definition of a horizontal asymptote. As x approaches infinity or negative infinity, y will approach that asymptote. So that's telling me what's happening at the ends of the graph. Then we also have this important piece of information here, that the graph will cross the horizontal asymptote at -10, 1. So this point right here, the graph crosses the horizontal asymptote. We also have 0, -2 being a x-intercept. And then we also have the ordered pair 0 and -1/9, which will be about right here. So this is all the information that I have on the graph right now. I don't feel comfortable drawing the lines yet. What I like to have is in each section, I'm going to label the sections. This is a section here, and I have 1 point in that section. And this is a section here, and I have 2 points. And this is a section here, and I don't have any points. So I want to make sure that I have some points in each section so that I know how to sketch the graph. So I definitely need a point in this section. So I want a point that is greater than 6. But I also feel a little bit uncomfortable since the only point that I have in this section is on my horizontal asymptote. I'd like to get another point so that I'll know how to draw the graph going towards the vertical asymptote. So I really need a point that is above or below that horizontal asymptote so that I know whether I should be drawing my graph going to infinity or to negative infinity. Right now I don't know which way to draw it. So I'd like another point in that section. And in this middle section here, I am satisfied with the points that I have here. I don't need any extras to know how to draw the graph. So what I want to do is I want to go to plotting points method, where I choose x's and find the y's. So I want to make sure that I choose a point that is less than -6 and also a point that's greater than 6 so that I can fill in my missing information. So let's pick maybe -7 and +7. So we're going to substitute these into our function. So I've got -7 plus 2 times -7 plus 2 over -7 squared minus 36. So -7 plus 2 is -5. So we have -5 times -5. -7 squared is 49. So I have a positive 25 on the numerator, and in the denominator, 49 minus 36 would be 13. So this is almost 2. Not quite 2, but almost 2. We'll do the same thing with 7. We have 7 plus 2 times 7 plus 2 over 7 squared minus 36. 7 plus 2 is 9. 9 times 9 is 81. 7 squared is 49. 49 minus 36 is 13. And 81 over 13, oops, I multiplied instead of divided. 81 divided by 13 is just a little bit more than 6. So we've got two ordered pairs, -7 and 1.9, and 7 and 6 point about 2. So these 2 points are going to help me draw the graph. So we're going to add them to our picture. We have -7 and 1.9, which is about right here, and 7 and 6.2 would be about right here. So now that I have those extra points, I feel comfortable drawing the lines, and I'm going to use those definitions of the asymptotes to help me draw the line. Remember, they act as guides, almost like fences. You want to draw moving towards the fence and also going to infinity. So starting with the rightmost point, that point 7, 6.2, I'm going to approach the vertical asymptote going towards positive infinity, and going towards x going to infinity, my y will approach that horizontal asymptote. In the section in the middle, I'm going to approach negative infinity on both sides, and on the left-hand section, on this side, I'll approach infinity. On this side, I'm going to cross the asymptote but come back to that horizontal asymptote. Thank you for checking out my videos. Have a great day.